Shall we start?
Yes, ma'am.
Yeah. I think since it's the evening time, everyone finds difficulty in continuously attending 3 hours.
Yes, yes.
Yeah, after reaching home, lots and lots of work pending. Okay, anyway, yeah. So let me share the screen.
Yes, ma'am.
Is it visible? Okay. Yeah. Now, let me share a small research work, of course, done by me. Yeah. Here, actually, of course, the objective is to introduce a new variant of GAN. But variant of GAN here, not based on those issues, but instead based on specially handling data. Okay. So simply the objective includes to develop a novel technique in GAN to improve performance of deep learning, then to design a new framework with a concept heavy tail distribution. So that itself is a new word. Okay, what is that? Yeah, let me start with the motivation of GAN. Even though I mentioned what is GAN, what is generator, what is discriminator, then types of GAN, etc., etc. So the main motivation for the design of GAN, of course, it is that the learning process requires neither approximate inference nor approximation of a partition function gradient. Okay. Now, most of the here, simply saying, I can show you with the architecture. I'm going to make a change here. That's all. The new technique which I am going to introduce is here. I don't know how many of you remember I mentioned here Z is a sample from a probability distribution, and in traditional GANs and almost all GANs, this Z is from normal or Gaussian distribution. I am going to change that assumption. Instead of that Gaussian or normal distribution, I'm going to change it as one other type of distribution, it's a non-Gaussian, of course, heavy tail distribution. Okay. Now come to this. I'll explain that. Before that, some basic concepts. Okay. So most of the why I approached that, I took that approach. So most of the virtual sample generation methods are based on the assumption that data generally follows Gaussian or normal distribution. However, in many cases, you can just imagine, if I'll provide you a data set, if I'll ask you to draw a graph for that, in most of the cases, you will not get a normal shape, right? Yeah, that itself is a reason. So in many cases, data set behaves Gaussian as well as non-Gaussian. In many cases, it's actually a combination of those. So in such cases, distribution of samples generated by the traditional method would change. Of course, GAN models usually assume that the real sample data follows Gaussian distribution. That is, in the traditional GAN, actually two assumptions there. Here, we are actually we will fed some data set to the discriminator. So we are providing a set of input features here. That also follows normal distribution. And here we assume Z is a sample from generated samples. We are generating samples from normal distribution. Okay, so I am going to change these two assumptions. Okay, so GAN models usually assume that the real sample data follows Gaussian distribution or normal distribution, but the system may be disturbed by some other noise, particularly heavy tail noise in many cases. What is heavy tail? Nothing. You all are familiar with normal curve, right? This curve, normal curve. Okay. Heavy tailed means more data. This is actually tail part of the curve. This part and this part. Okay. So heavy tail means tails are heavy. So more data will be scattered over this part and this part. Of course, some negative heavy tail distributions are there. Heavy tail itself classified into right heavy tailed and left heavy tailed. So you don't have to bother those things. So difference between heavy tailed and normally, I think I have included a picture with that also. What is the difference between?
Is it similar to skewness? Like,
Yeah, skewness. But skewness, of course, if the data is not normal, then we say that it is skewed. But under the skewed itself, skewed distributions, lot of distributions are there. Okay. So this heavy tailed is one among that. Got it?
yes.
Okay. If the data is not normal, we say that it is skewed. Lot of skewed distributions, probability distributions are there. This heavy tailed is one of the skewed distribution. But again, I am saying that there are distributions in which it is not skewed, but it is heavy tailed. What do you mean by skewed? One side is not the image of other, right? If it is not symmetric, we say that it is skewed, right? If it is not symmetric, that is, if we draw a central line here, one side is the exactly image of other. See, this is a skewed. But there are distributions in which symmetric heavy tail distributions, because now in all it is not necessary that all skewed distributions are heavy tail distributions are all skewed. It is not necessary that heavy tail distributions are all skewed. Say for example, take the case of this one, green one. See, this we call it as Laplace distribution. This is a, so by looking at that, see, if we draw a center line here, of course, exactly one side is the image of other. We can say that it is symmetric, not skewed. But this is a Laplace, this is a heavy tail distribution. That is why I mentioned some skewed distributions are heavy tailed. That I agree to that. Say, for example, this one. But it is not necessary that all the skewed distributions are heavy tail, but otherwise heavy tail distributions include both skewed and non-skewed symmetric distributions. Okay, yeah. The meaning is that heavy tailed means, tail means this part and this part, more data scattered over this part. See, suppose whatever that content or whatever data here, the number of data, say here, same number, if it lies this side also, we can say that it is not skewed, it is symmetric, which is a case of Laplace. Got it? Someone asked me about skewed, difference between skewed.
Yes, ma'am. Yes,
Is
ma'am.
it clear?
Clear, ma'am. Yes.
Okay.
Thank you, ma'am.
Okay. Yeah. Okay. Yeah. So coming back to this, so GAN models usually assume that this data or real sample data follows Gaussian distribution. But in most of the cases, just imagine a situation. If I'll provide you a data set, if I'll ask you to draw a curve using that data set, can you conclude that always is it possible to confidently say that you will get exact normal distribution? Maybe sometimes you may get, but in most of the cases, you will not get that data normal curve. So that is why I said the system, in most of the cases, system may be disturbed by some noise, particularly heavy tail noise. In many data, especially industrial data, then we can see this financial data, then economics data. In economics, there we can see the heavy tail distribution has more application in this financial data. I don't know how many of you have heard about Pareto distribution. Pareto distribution, actually it is known as income distribution. It's very useful very useful in financial side, as well as econometrics, I can say. So this Pareto distribution is one of the popular heavy tail distribution. Pareto distribution is almost symmetric, right? So it is a heavy tail distribution. A lot of heavy tail distributions are there. I'll come to that. Data usually show the character of heavy tail. So this is one of the reason actually I took an initiative towards this work, or in this particular context. Okay, so let me speak, since most of you are from computer science background, are not familiar with this type of distribution. Let me say a few words on this heavy tail distribution. Okay, so if the behavior of data is dominated by large values and the probability of exhibiting a huge value is relatively big, then that kind of data we call as heavy tailed. Or we can say another word for this one is power law distribution. So that heavy tails or power law, that refers to actually the tail probability. Simply saying that tail probability decays to zero at a constant power rate of the value of observation, in contrast to the exponential rate. That simply saying heavy tails means it's a characteristic of some phenomena where probability of extreme values is large. Maybe I'm not focusing much on the mathematical concept, that may be confusing for you. Simply saying, if that tail is heavy, more data is scattered towards that tail part, we can call that the data so that data follows heavy tail distribution. Okay, then while comparing with the normal distribution, we can say probability of density curves of probability distribution curves of heavy tail distribution and Gaussian distribution are almost similar, which are bell-shaped curves, but the tail of probability heavy tail distribution is thicker. Tail, this part. Okay, this part is more thicker. See, by looking at this figure itself, maybe you will think this is a normal distribution. No, no, no. This is a heavy tail distribution. Okay. Okay. Again, by looking at a curve, it is not necessary that always we may be able to reach a conclusion in which the data, corresponding data follows heavy tailed or not. So we have some mathematical things to verify that. If you are given a data set, you have to check whether that follows normal distribution, heavy tail distribution or not. Please find this limit approach. Use this. Either you can use, this is quite difficult to evaluate, because it's finally we have to simplify that expression, and finally if you get it as infinity. But this is the better way. E power minus tau x, x is actually our values, divided by probability that x greater than x. Survival function, actually denominator is actually survival function. If you can evaluate simplifying it and apply the limit extends to infinity, if you get it as 0, then we can say that that corresponding one follows heavy tail distribution. But there are other ways. This is another way to check whether the data follows heavy tail or not. Data or data distribution, of course. Or by simply drawing the figure, if we are able to catch that, then it's okay. Okay, anyway, the probability distribution curves of heavy tail distribution and normal or Gaussian distributions are similar, but both are of bell-shaped. The difference is that the tail of heavy tail distribution is thicker. That is the data at both ends, this end and this end. Data at both ends of heavy tail distribution is more than that of Gaussian distribution. That is a condition. And we say probability of extreme values is greater. Extreme values means here probability of extreme values is higher. So that, of course, aggregated tail makes this data cannot be ignored. Okay. So if these models are directly used to train non-Gaussian data, then the gradient, of course, may disappear and tails become shorter.
Ma'am,
Yes, please.
ma'am, if the distribution of the data is like heavy on both the side, like there it might affect the variance and bias, right? I mean, how would we try to balance out
Exactly.
variance and bias?
Exactly. It will affect its variance. Definitely, no doubt in that. There are certain mathematical things to resolve that. Okay. Definitely, you are right. But mathematical properties are there. One popular book there, if you are interested, you can have a look at one popular book, Asymmetric Laplace Distributions. Asymmetric Laplace distributions, actually, this is one of the asymmetric Laplace distribution. This is actually a particular case of asymmetric Laplace distribution. See, this is Laplace, right? See, this green curve. Okay, asymmetric means this is actually when we draw a line here. Of course, one side area is exactly same as the other side area or probability. But asymmetric means if we draw a line here, the left side area will be different from right side area. Asymmetric Laplace. So that other name actually Kosubowski. So why I mentioned that book? In that book, actually, it clearly stated all the properties related to variance, etc. Okay, that is how do we resolve that? Okay.
Yes, ma'am.
Yeah.
Thank you, ma'am.
Okay. Yeah. So where we stop? Yeah, here, this slide, right? Yeah. This one. Yeah. So the distribution is said to have a heavy tail when the decay of probability density function that is lower than Gaussian distribution, and the tail of heavy tail distribution is thicker than that of Gaussian or normal distribution. And also one more thing, this thickness of tail can be measured by tail index. There is a concept tail index. Different tools are there for measuring the thickness of tail in heavy tail distributions. Tail index actually it is equal to order of highest absolute moment. See, this moment is actually closely related to that question which you asked. One participant asked, no. Moment is actually two types of moments are there in statistics: central moments and raw moments. Okay, so here itself that is finite. See, which is equal to have order of highest order moment, that is finite moment, so finite variance. Okay, moments actually two types are there: central moments and raw moments. Second central moment is same as variance, and the first raw moment is same as mean. Okay, just I mentioned. Okay, so the lower the index, heavier the tails. So there are various tools for measuring tail index. So that is again one of the another way, alternative way for checking whether the distribution is heavy tail or not. Okay, these are the mathematical ways for checking. Then either you can check using tail index or using simply this is a heavy tail distribution, histogram of a heavy tail distribution. See, I just connected only those points. This is almost similar to asymmetric Laplace. By simply looking at the figure, you may feel that, oh, this is symmetric. No, this is not symmetric. If you draw a line exactly in the middle, one side area that lies in the left side is not equal to the right side. Anyway, there are various methods for measuring this. Yeah, this is just a comparison of heavy tail distribution and other existing distributions. This is actually normal distribution. Blue one is Gaussian or normal distribution, but this green one is Laplace, which is a heavy tail distribution. Then here, Gaussian and another heavy tail. Blue one is Gaussian. That is why I mentioned by simply looking at the figure, you may not be able to, not you, my side also, we may not be able to distinguish between a heavy tail and normal distribution. So in that case, you can approach a mathematical way, or you can measure the tail index. This is actually log normal distribution and normal distribution. Yeah, see, green one is normal distribution. Hmm? Red one is log normal distribution. Where log normal distribution is a heavy tail distribution, so which is purely skewed. Look at this green figure. This is not skewed, but it is a heavy tail. Look at this red figure. This is skewed, but it is a heavy tail. So heavy tail includes both skewed and not skewed, both skewed and symmetric. Okay. Now this is actually standard normal. Blue color is now standard normal. Red is Cauchy. Cauchy distribution is another heavy tail distribution. So that is why I mentioned, by simply looking at the figure, it may not be able to reach a situation, or it may not be able to say always the distribution is heavy tailed or not. So we can check this condition. Usually we check this condition. Some integration or discrete heavy tail distributions are also there, not only continuous distributions. Okay. Now, what is the relation between exponential and heavy tail? Heavy tail distributions are distribution, of course, tails are not exponentially bounded. Heavier tails than exponential distribution. See, this blue is exponential towards this x-axis, right? But some sound is coming. Okay, so this blue is exponential towards this axis, but green is towards like this. Okay. Now, these are the popular heavy tail distributions: Pareto distribution, Weibull distribution, Cauchy distribution, log normal, student's T distribution, asymmetric Laplace distribution, etc., etc. And one of the heavy tail, some literature review on this heavy tail distributions and GAN study. Yeah. So in this particular particular work, I am not using any of these distributions. Okay, I already mentioned. Just I want to share you one work done by me. Hmm. So these are the commonly used heavy tail distribution, and myself introduced a heavy tail distribution known as new generalized Pareto distribution. This is one of the heavy tail distribution. So anyway, after getting this expression, or this expression, so while coming up with a distribution means, actually, since you people are from almost all of you are from CS background, just I can say one word on that. See, usually what people do is that, say, CS from the computer science side, I'm also working like that, of course. What we do is that we will get a data set, we will be provided with a data set, we will try to model that data set, right? Even for to come up with new variants of GAN also. Using the data, we always start with the data set, right? But in mathematics as well as statistics research, it's not pure statistical or mathematical research, it's not like that. We will derive different concepts using the existing things. Okay, then we had to say, for example, to introduce a new distribution, say for this one, new generalized Pareto distribution. I have not started with a data set. From the literature review, some derivation is there for this, for getting this. Okay, some derivation is there behind this probability density function. So I have raised this concept, this expression, equation number 6, or equation number 7, distribution function or density function. Usually we come up with, we will derive that, but some genesis there. Okay, so after getting this, we have to ensure that this is a probability density function. We will verify the properties of probability density function, or we will verify the properties of distribution function. Then we have to check the graph. This is the graph for different. See here, actually I have some alpha, beta, theta, gamma, 4 parameters. X is our variable, random variable. So 4 parameters here. By giving different values for these parameters, that is one way of verification. We have to get the shape of heavy tail distribution. Then the condition for heavy tailed. Okay, I have to verify that. I have verified that condition, that limit of e power minus. It's very easily to, not that much easy, but I have verified this condition. Okay, that is equal to 0. Then after verifying that, after conclude verifying that it's a probability density function, then we can move to explaining or deriving properties such as mean, median, mode, etc., etc., etc. A lot of things are there. I'm not going there, but anyway, a lot of properties are there. But finally, we will come up with data analysis. What we do is that we have to find a data set, just the reverse process that you are doing. Other branches, not only in
Ma'am,
CS, other branches, people are doing like this. We will start with a data set and finally we will come up with a model. We people in the sense, usually mathematics and stats, we will do the reverse of that. We will take a data set, first check whether it follows this NGP distribution or not. Never follows. Actually, we ourselves prepare a database itself. First, we have to check the data set. Even I can say, I think I can show you that paper, then it will be easy for you. Let me check. I don't know now whether it's available now, Google Scholar. Can you see my screen?
yes, ma'am.
I'm searching Google Scholar. Can you see that?
Yes, ma'am.
Okay. Let me check that. I don't know it's available or not. Really. In my personal laptop, it is there downloaded one. That's why. Yeah. I can see. Yeah. This is the one which I explained. See. Can you see this paper? This article?
Yes, ma'am. Yes,
okay.
ma'am.
Yeah. See, first actually, okay, let me skip that introduction. Yeah. See, I had derived this expression, but for getting this expression, sorry, not this one. Sorry. Where is that? Yeah, this one. PDF of NGP. Okay. For getting this expression, actually, some theoretical concepts are here. Okay. So first get an expression, then some properties. These are the properties. Some properties, then graph, prove the graph. Then these are the properties again. Structural properties, mean, median, mode, variance, etc. So that is why previously I mentioned for each of these distribution, we will derive mean and variance and we will verify the properties of that. This is mean and variance for different values. Then another property, Renyi entropy, Shannon entropy, characterizations are there. Okay. For just I want to, this is another property. Okay. Yeah, this is actually time series modeling with that. Yeah, this is the data analysis. See, I have not started. We have not started. We are not usually starting with the data analysis. After deriving or after proving all the properties, then we have to search for a data set that follows this particular distribution. Okay. So this particular data set, even I'm getting this data set after say some 1,000 or 2,000 data set. Okay. Anyway, so using this data set, what we do is that, see, these are the good. Simply getting a data set, find a data set that matches with the distribution. The part is not over. First, we need to find out a data set that exactly matches with this probability distribution. Then these are the goodness of fit, for various goodness of fit criteria for proving or to prove the superiority of my probability distribution with other models. Say, for example, I have computed AIC, BIC, I think some of you are familiar with these values. AIC is Akkei information criteria, BIC is base information criteria, AICC corrected Akkei information, KS is Kolmogorov-Smirnov. The thing is that I have to get these AIC values as lower than, see, this value is actually for my distribution, these are some other distributions. I have compared my ASE value with some other distribution. So in this column, actually, I am getting minimum value. So that I can say one criteria satisfied. Then similarly, here also I am getting minimum value. Here also I am getting minimum. So whatever be the number of criteria, if I increase the number of criteria, acceptance would be more easier. Anyway, so that is the case with, yeah, this is another way for of proving the superiority. That is using the data set, draw a histogram with fitted PDF and the other data. Anyway, just I want to share that. Okay, so here that same distribution, since it's my work, actually I have used that same distribution to generate a new type of GAN known as new generalized Pareto generative NGP GAN. Then now what is the difference? So here, so where we stopped, yeah, okay, so the challenges here actually includes, or I can say okay, the challenges includes actually, of course, the existing GAN do a poor job of matching the asymptotic behavior of heavy tail distribution. Then Gaussian prior distribution cannot be used to simulate heavy tail samples, especially while dealing with infinite moments and large distances between outlier points that are characterized by heavy tail. Of course, loss functions may produce unstable or near zero gradients. So a heavy tail GAN, specifically NGP GAN, leverages extreme value theory. I don't know how many of you are familiar with that. Some extreme value means that n values, highest and lowest values, and the functional properties of neural network to learn a distribution that matches asymptotic behavior of marginal distributions of the features. Okay.
Similar to min-max?
Not similar to min-max. Not
The extreme value theory?
exactly similar to min-max. Actually, extreme value distributions are there based on different concept. One among is this case, min-max. Only one. It's a particular case only. Okay.
Yes,
Yeah.
ma'am.
Yeah. Now, so this is actually the problem statement to propose a new framework of GAN known as new generalized Pareto GAN. New generalized Pareto generative adversarial network with input noise as heavy tail distribution, so as to generate more samples on the tail of data distribution and detect anomalies near the support boundary. So of course, a study on that theoretical aspects also considered. Then of course, to apply the new method to a heavy tail data set. So before moving to that architecture, just a look at the mathematical expressions for this new generalized Pareto distribution. This is the probability density function. It is very clear that it contains 4 parameters. If we take the case of Gaussian or normal distribution, you have only 2 parameters, mu and sigma, or mean and variance. But here we have 4 parameters. That itself gives the flexibility, data flexibility in modeling. Then cumulative distribution function, then survival function. This is the curve. Yeah, this is a simple architecture, not that much change in the architecture. So that is why previously I mentioned I focused more on one side, especially the characterizations or properties, mathematical properties, and other side, the flexibility in data modeling, of course. That is the CS part. Okay, so here the distribution of hidden variable, that random noise, Z is changed to NGP, that is a new generalized Pareto distribution. Okay, which is one of the heavy tail distribution. All right. Now, using this NGP distribution as prior distribution or random noise Z is simply saying the random noise Z is a sample, or is that sample Z is a sample taken from NGP distribution. That's all. Okay. So using this NGP distribution as a prior distribution, of course, that can increase the probability of network learning to the tail of distribution, to the tail distribution. No doubt in that. That remaining, even though remaining steps are same, look like the training process same, but there are changes in loss functions and other things. because simply changing normal, this normal to Gaussian, sorry, normal to non NGP distribution means don't think that, oh, all other things are same. No, no, no. All the mathematical things are different. The training process itself, even for, say, for example, case of loss function. Okay, here actually I have used this. Have I included that? So these are, see, based on this Lipschitz continuity, Lipschitz function. I think some of you might have heard about JS, Jensen-Shannon divergence case. So we are not in a position to use that, or Weierstein loss function. Nothing, nothing. Weierstein distance also, it also fails here. So here actually I have used a loss function based on a mathematical measure known as Lipschitz condition. So actually for getting that, I have proved these mathematical properties, mathematical theorems. I'm skipping these properties because, yeah, coming to the data. So here actually I have considered a data for industrial data set purely. Data for anomaly detection is considered here, where it contains issues and advances in anomaly detection evaluation for joint or human automated systems. And here data set includes 20 kinds of fault data. Each sample has 555 variables and each fault has 960 samples. Okay, they are named as fault free training, fault free. Okay, yeah, not in Kaggle. Somewhere I included that link here. Okay, anyway. Yeah, just a description of, say, column 1, fault number that ranges from 1 to 20 in the faulty data sets that represents fault rate. Just a description of columns 1, 2, 3, 4, etc. So column 1, 2, 3 actually defined separately, and column 4 to 55 contain the process variables. That column names retain the original variable names. Okay, so the first thing which I have done is that, see, to apply for this particular type of GAN, definitely two things I need to consider. First, I need to assure that my data set follows heavy tail. Let me go back to the traditional GAN so that it will be easy for you to understand. Yeah, this is the traditional GAN. See, two things I have changed here. One is this input features, that is the data set which I started with here for analysis. I have to assure that this follows heavy tail distribution. That is the first thing. If it heavy tail distribution, then I can pass on. Second thing is that this random noise Z is a sample from a probability distribution. That probability distribution also, I have taken this new generalized Pareto or NGP distribution. Those are the two things I have considered in this study. Now moving back to, yeah, okay, data. This is a simply explanation of the data set. So this is the heavy tail, that distribution of that data. Okay, so which clearly shows that it follows heavy tail distribution. It exactly looks like almost this one. This is actually this also, only difference is that this is also actually generated from that data set. Only difference is that here actually I have normalized. That is the only difference. So other one is direct one. Yeah, that is another case. If we want, we can scale, not normalize, scale that data set. Here actually I have done that. For scaling that, we can use either min max. Here min max transformation steps, actually in the steps used for training this type of GAN, I have used min max transformation with a range from -1 to 1. Then load the data into appropriate GAN for training, set the learning rate to 0.0002 and batch size 64. Just I am showing you only the things which I have used here. It is not necessary that you can use only this value or batch size 64. That depends on you. Then for steps to generate data from NGP GAN are generate random noise samples from NGP distribution, pass the noise values to the appropriate GAN model, then apply inverse transformation on the generated data to final output. So just a word on training GAN. So here actually both generator and discriminator utilizes here to assert some context, actually to at some extent actually I have used DC GAN also here. So that is why some convolutional network concepts I need you. So that is why previously I mentioned, don't think that simply changing this normal to NGP it is very easy to train. No, 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 no. Lot of uh, even I took around, I think, one year to finish this. Okay. So based on different because in so many places actually I got stuck, especially for convergence case, then loss function, etc., etc. Okay. So these are some steps that I followed for during the training. Okay, this is the loss function. Okay, so as I mentioned, here finally I reached a loss function based on LS GAN, that is least square GAN. Okay, and this is closely, this loss function actually is closely associated to Lipschitz condition in mathematics. Okay, yeah, then now some results. Yeah, various features, distribution plot of training data. Then this is actually distribution of features. Only 1 to 15 I have included in the slide. I'll show you that file also after this. Okay, then this is cumulative sum of the features, only 1 to 15. 1 to 15 included in the slide, but remaining things are also there. Simply descriptive statistics. Then yeah, so here actually mainly see GANs, of course it is somewhat similar to variational self-encoder as a deep generation model. uh, and here basically I have considered different parameters for generating results. Actually that includes mean, the standard deviations, skewness, kurtosis, etc., etc. So this is actually graph of log mean and standard deviations of real data versus fake data. Then skewness and kurtosis here of generated data is this one, and real versus generated data almost looks like same. Yeah, this is actually histogram. In this slide I have included only randomly feature one. See, this is histogram of actual data, histogram of generated data almost look like similar. This is for the feature 3, histogram of actual data and histogram of generated data almost look like same. Then loss over epochs. Yeah, finally accuracy, of course. DC GAN I compared with the DC GAN. DC GAN actually 0.71 only, but look at this NGP GAN 0.93. Weeble GAN, Weeble is another heavy tail distribution. Okay, so from this definitely we can say that heavy tail will give good results, that which clearly shows that potentiality or superiority of the result. Yeah, now let me just take quick, what is the time now? Yeah, a quick look on that practical also. Then I'll give time for question answer sessions if any questions. Okay, first let me open a basic GAN. And please keep in mind, actually, this for GAN training, for practicals, either you can proceed with PyTorch, or for some cases, Keras, TensorFlow Keras, it's okay. This is actually how to train a GAN, a basic one. Okay, so first part, importing libraries, all those things, define. Okay, then this library stores, import all these things here. Then this just MNIST data set. Okay, so from data set, from that torch itself, import MNIST data set. I think almost all of you are familiar with that. Then epochs, all those things I mentioned here. Now the components, we have two things, discriminator and generator. So this is actually the case of discriminator. So those who are familiar with deep learning only will be able to get it, catch it very easily. Okay. Then this is the discriminator case. Then generator. Okay. Define the generator case. This one almost similarly small difference. Okay. These are all familiar to you. Those who are familiar with especially CNN or any deep learning deep neural networks. Then loss function for training can define the loss function, discriminator loss, generator loss, then generator loss here, discriminator loss here, then load data and initialize, load MNES data set. See, here I am loading data, then train GAN. So this is the main thing. Okay, generator loss 0, discriminator loss 0, then epoch 10 started with 10. Then training, generator training part is this thing. Okay, sorry, generator, discriminator, train discriminator and train generator. Okay, so here I can like this, generator loss. Okay, finally how to generate data set, that also I'll show you how to generate. Yeah, generate samples, finally generate samples. So this is actually a simple GAN. Okay, now I can show you the program for that particular work, research work. Okay, yeah, start with importing all the libraries. And here I have proceeded with TensorFlow Keras. Then scale data. So that is why in between I mentioned in most of the cases, since usually we, even those who have done this different data analysis, you might have started with the standardization or normalization. So this is not a normal distribution. This is a non-Gaussian distribution, non-normal distribution. That is why I have used for transformation min-max scalar. For scaling those, then convert to TensorFlow dataset, then load the dataset, loading, then define generator and discriminator classes here. Define generator and somewhat similar to the previous usual training GAN. Only difference is that here actually I used Keras. Previously I showed you PyTorch. Okay. Then define discriminator and generator part here, discriminator part, then GAN. Okay, create the generator and discriminator, compile discriminator and GAN, then training steps, all the things. Finally, okay, plots. For plots, actually, I have done these things additionally. Okay, for increasing the length of plots, all things. That's why some additional things are there. Okay, charts, because now lot of the charts plots are here. Then metrics, discriminator loss, generator loss, discriminator accuracy. Okay, then regarding the parameters, okay, yeah, box model train, I can say, yeah, here for loss or plot metrics, then generate synthetic data. I have generated the data. Here actually I have calculated the mean of different variables. Here, see, left side you can see descriptive statistics such as count, mean, standard deviation, minimum, then first quartile, median, first quartile and third quartile, or lower quartile and upper quartile, Q1, Q2, Q3, like that. Then again, for the remaining things, yeah, this is actually same. Yeah, this is actually actual data. I have computed the actual data, describe these characteristics or these properties of actual data, and here it is generated data. So we can see that some similarity here. See, for example, count is same, 0.7371 here. Here actually I am getting 0.75 generated data, somewhat near to that. Okay, all the values we can't, but almost. Okay, then remaining plots. See here actually all the variables I have plots. In the slide actually I have included only few. See here full things here. Slide only one slide I have full things here. Okay, Then that distribution features also. Here also distributions also over all the features. See different features. Yeah, that's it. So anyway, this GAN actually, it is not that much easy to train. Whatever be the types of GAN which we are considering, right? Everywhere you can see those who have dealt with GAN, you might be familiar with that word. GAN is difficult to train. Okay, so now the platform is open to queries. I know this is those who are not familiar with this area, it's not that much digestive. It's not taking a session on, not similar to taking a session on machine learning or deep learning or some deep learning techniques or something like that. But those who are doing research in this particular area, GAN, especially in GAN, I'm not talking about the probability distribution. I showed you, since I explained different variants of GAN, I showed you a new work also. That's all. Just to share you that not only from the data side, from the theoretical side also, it is possible to come up with new variants of GAN. Okay.
So, any queries?
Ma'am?
Yeah, tell me.
Yeah. Good evening, ma'am. It was a wonderful session. Thanks a lot, ma'am. Ma'am, ma'am, with respect to the research area, especially with respect to GAN and deep learning, as well as these transformers, ma'am, which are all the statistical concepts we should focus on, like
Which are,
technically
I'm
as
not
well as
getting, pardon?
which are all these statistical concepts or features we should focus on
Correct.
while training the model or while trying to make the model more, efficient.
I can't give you an answer in one word because lot of things are there in this 2.5 hour session itself. I mentioned many things. Say initially three issues I mentioned. No, case of one is the case of gradient, dealing with gradient. Okay, so while dealing with gradient, lot of mathematical things are there behind that. Okay, using that, try to resolve some of the existing limitations so that you can come up with new types of GAN. Then regarding what is mode collapse, that is another thing. Then convergence case, already I mentioned. I think you I don't know, one participant asked doubt
Yes,
on.
ma'am. Convergence case. Yes, I was.
Yeah, convergence case. Now also with existing GANs also, there are some limitations for this convergence rates. So if you just make a literature review on that, you can find that. So on one side, actually, this work actually I have carried out to a certain extent only. I'm not able to resolve all the things, but the thing is that no, when even though we started with resolving that, while that research is progressing, maybe that may not be able to resolve all the issues related to pure convergence, but I will focus on the convergence of my particular variant of GAN. Okay, but mathematically speaking, if someone wants to take effort on that, you can come up with a common solution for that. Okay, yeah.
Ma'am, if possible, can you please share your research work, like a link of your research paper
Which one?
for reference?
Yeah, sure. Simply you can type on this new, I showed you, no, new generalization of NGP. That's all. New generalized Pareto distribution. New generalized Pareto distribution. Simply Google search. New generalized Pareto distribution. It's actually published in Communication and Statistics. It's a SCI journal. Okay. Any other query? Since this is the evening time, that is why in between I was looking into my watch.
Mhm.
I have to keep time management. Otherwise, others will not. I'm not tired, but hearing participants.
Ma'am, I have a question.
Yeah, please.
Related to your research work, how many epochs it takes to get converged to that minimal error, or how many epochs it took to get
Yeah,
converged?
actually, I took only some 200 something. I can share you exactly. Just a minute. I think 200 only. Some 200. Yeah.
200 is a big one, right? I mean,
No, no, two. I start final accuracy. No, 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 no. Ah, yeah, yeah. 200 big one. See, one night we may take one full night. Yeah, that is why I mentioned I took around 1 year to finish this paper.
oh, great. Thank you, ma'am. Thank you.
Yeah, even I am not saying that this paper got published in the first submission. No, 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 no. I think the first two articles are rejected. Third one only. But the thing is that even though it will get rejected, no, we will get some points to improve that from that review. No, we will get some points to improve that.
Okay, thank you, ma'am.
Yeah. Any other queries?
So, shall we conclude? Participants, any queries?
Any query? If nothing, of course. I think nothing.
Okay.
We can
So,
conclude. Okay. Thank you once again. Thanks to all the participants and the organizers, Prida ma'am, and other coordinators, Ilyas
so
and Vishnu
let
Priya.
me conclude, ma'am. Okay.
Yeah,
On behalf of
sure.
the Department of Computer Engineering, College of Engineering, Cherthala, and participants, I would like to extend our heartfelt gratitude to Dr. Bindu Krishnan for accepting our invitation and for taking time to share her expertise on generative adversarial networks with us today. Your insightful presentation has not only deepened our understanding of GAN, but also inspired us to explore new possibilities in the field of deep learning. We appreciate the effort you put into making the session interactive and engaging. Despite of being an online session, your enthusiasm and passion for the subject are contagious, and we were grateful for the valuable insight and hands-on experience you shared with us. I request all of you to please join me in thanking Dr. Bindu Krishnan for her time, expertise, and generosity in sharing her knowledge with us. We look forward to applying the knowledge gained from this session in our future endeavors. Thank you once again for your time, expertise, and enthusiasm. We wish you continued success in your endeavors. Thank you, ma'am. Thank you. Thank you so much.
Thank you. Thank you. Thank you.
Thank you, Vidhu ma'am.
Thank you,
Thank
ma'am.
you. Thank you. Thank you all.
So, I would like to thank all the participants once again for joining us today. As all of you know, tomorrow is our last day of the 6 days FDP. So, as we wind up today's sessions, uh, I would announce that tomorrow is the final day for FDP, and you are all aware that there will be a test scheduled tomorrow, and our session will start tomorrow at 2 p.m. Our session starts at 2 p.m. Please remind, tomorrow session will start at 2 p.m. So we will join at 2 p.m. tomorrow. And there will be a test at 6:30 p.m. Thank you all.
And the program ends at
Yeah.
8 o'clock.
Yes. So if you have any queries, you may ask.